Teacher knowledge and behavior is the component of the model that focuses on teachers' knowledge of students and content and on their expertise in classroom management and pedagogy. Teacher knowledge is the element of teacher knowledge and behavior that encompasses knowledge of student characteristics and teachers' in-depth content knowledge, and the blending of these to enhance learning. More information on this can be found in the Technology as Facilitator of Quality Education model. The students in this 9th grade algebra class are learning about quadratic functions. The teacher gives the students a worksheet that will help them discover the factored form of quadratic equations. The teacher shows knowledge of student characteristics by giving the students opportunities to use their interpersonal intelligence. The students work in cooperative groups, with each student taking on a specific role. The students have to work together in order to complete the worksheet.
Before we break off into groups, I just need to review those two things over there on the wall. We have group guidelines. Whenever you're in your groups, remember to be courteous, contribute, be sure you're listening to one another. That's very important. I think most important is that last one that we've talked about before. You stay on the particular problem that you're on until everybody in your group understands what they're doing. Then you move on to the next one. Okay? And then the group roles that we have are listed over there also. You have to decide as soon as you get into your groups who's going to be the reader, which one of you are going to be the recorders, which one will be the coordinator, and which one will be the leader. Reader, you have to read through the problems.
Then graph the polynomial using the zoom z decimal and list the x-intercepts of each.
Not the factor form, though. Or wait, yeah, we do.
Yeah, we do. It's just the x and then
We're supposed to like actually graph it and make a
I think so.
Okay, so we graph it so it'd be...
Well, the equation would be
that's what it looks like,
plus 4
right?
and then x minus 4. That's what it looks like.
The teacher's in-depth content knowledge is evident in the methods of instruction she uses. The teacher recognizes the effectiveness of group work. The students in each group collaborate, combining their skills and knowledge to solve the problems on the worksheet.
This is what it looks like with the same thing. It's one line.
Right.
So that's all we're going to draw.
So you just draw a straight line from, like, right here.
It's 6 down this time.
Down through 1. About half.
And the x-intercept is 1 and 6.
How do you know that?
Because I zoomed out, and plus it's going to be the opposite of these two. It's going to be positive 6 and positive 1. This one was 4, so it's a negative 4. This one's 5 plus 1. That's a good equation. Okay.
Oh. That would explain things.
Should we just make a line?
Are you ready? Yeah, if you want to check that.
Yeah.
I think I did it.
What do you have?
What's the x-intercept?
1
It's the
and
opposite
6.
of what these are here.
Yeah, it's going to be the opposite of what's inside here.
So if it's negative 6, it's going to be positive 6. And if
If
it's
it's negative 1, it's going to be positive 1.
Wait, that one was -4, and you said that was
And then
-4.
it's,
No, it's
no,
positive
it's
4.
positive 4 and this one's negative 4.
The teacher's interactions with the students during group work allow her to give the students guidance without giving them the answers. The students are responsible for coming up with their own solutions.
Did you discover anything up to problems number 1 through 5?
Yeah, it's the opposite.
Say it again, either.
The x-intercepts are you put those in this is the opposites.
Okay. So I haven't asked anybody to do this yet, but you see you have the factored form listed on the board. What do you think that equation would look like? Y equals what?
Equals the opposite of this number. The opposite of that number. Yeah.
Think you could come up with a form then?
Equals x minus.
Let's call these roots. Remember we talked about x-intercepts being the same thing as roots? Let's call this having a -4 root and a positive 1 root.
Okay.
We can use the variable r then.
Oh, what? 2 r's or?
You can designate them as R1 and R2.
Okay, -1, 1.
Okay, do you guys see that? He wrote y equals x minus r1 and x minus r2. Ray, did you see that?
Yeah.
Okay. So what I think you guys discovered there is the factored form of the equation. So now you can use that to answer your questions 6 and 7.
The teacher integrates discovery learning with group work. As the students work through the problems on the worksheet, they begin to see the connection between an equation in factored form and the x-intercepts of its graph. The students have the opportunity to actively construct their understanding of factoring.
And then general form, you just factor it back out. So
It'd be y equals
factor
x cubed squared. Sorry.
and then negative 3x, negative 7.
XX.
You do negative 3x plus negative 4x, negative 7x.
So it'd be negative 7x.
Minus 7x. You just plus 12.
Like, this is going all over my head.
Yeah.
For real, okay,
Moment.
do you guys got the
No, I don't got the
We don't got the
form
factored
yet.
form.
Remember, it's just the opposite of the two x-intercepts.
This
So
is
it'd be x
20
minus 3 and the x minus 4.
Oh.
Can we read that on the other side?
plus 12.
I'll be
So they're both negative, right?
Yeah, because they're
Right.
And
then
then you
what's
just factor it
general?
out, so then it'd be x squared,
X squared.
Oh, I see.
Oh,
okay.
and then the little thingy.
The teacher's in-depth content knowledge is evident in her transformation of the subject matter for the students. She ties abstract algebraic concepts to a real-world problem the students have to solve.
We are going to apply what we just learned. We are going to answer this problem. And it says, suppose you have 24 meters of fencing material and you want to use it to enclose a rectangular space for your garden. Naturally, you want to have the largest possible area for your plants. What dimensions should you use for the garden?
After the students have solved the problem, they look at their solution graphically. The students come to understand the real-world meaning of parabolas and quadratic data.
What is the real-world interpretation right now of x being 0, scroll down there to the left, and y being, nope, I can't, that's the best I can get. Who can tell me what that means right there? What's the interpretation of that? That's where you'd have the smallest area. Okay, right there. So what does this tell me about the problem I asked you? It says that if I have 24 meters of fencing, I should build my fence to be a 6 by 6 because that adds up to 24 and it would give me the largest area. It would give me the maximum point of 36. Okay?
The teacher extends the students' understanding of factoring through an experiment. The students use motion detectors called calculator-based rangers to find out how high they can jump. The experiment requires students to jump in front of the motion sensor while it measures the distance to the wall behind the jumper. The teacher displays knowledge of student characteristics by addressing her students' visual spatial intelligence. She has the students predict what the graph of the data collected by the motion sensor will look like.
What do you think, Taylor?
It's gonna go like that, and like it's like a plateau sort of.
You want to draw it? What you think? Good. Somebody want to try it?
Then the students test their predictions.
How can you tell from the graph when he jumped higher?
How far it is away?
Can you tell from the peaks?
No. How far it is like this one. The last one, like, he jumped the highest, the last one. As he was in the
Okay, so you think it was the last one?
yeah. It's like the how far the plateau.
I'm getting a lot of you talking at the same time. Can I have somebody summarize what you're saying?
The higher you jump, the longer you're in the air, so the wider that is, the longer time.
The higher you jump, the longer you are in the air. So the time difference from the start of the jump to the end of the jump should be longer.
The teacher again displays knowledge of student characteristics by giving her students opportunities to use their bodily kinesthetic intelligence. The students have to jump in front of the motion sensors to collect data for the experiment.
Told you, right?
Get up, Walter. Keep going.
Jump really fast.
The teacher shows knowledge of student characteristics by addressing her students' logical, mathematical intelligence. The data the students collect with the calculator-based rangers is linear, but they use a parabola to model the time the jumper leaves the ground until the feet return to the ground. The students have to apply their new knowledge of factoring to calculate their maximum jump height.
Now, here's what we're going to do to figure out your jump height, because this is measuring distance versus time. It's not measuring the height of your jump. There's a physics formula, and it comes from Newton's law of motion that is going to be on this handout that I give you. It's based on the force of gravity. It's an equation, and the equation is in the factored form. Okay? And what we're going to do is we're going to place a parabola, so to speak, on these peaks. Because the parabola, if I'm able to put a parabola here and here, what will the x-intercepts of that parabola tell me? The time. And the formula requires you to fill in the time. Fill it in for root 1 and for root 2. And then do all the math, and then the y value that's going to result is your jump height. Who has calculated some jump heights already?
We have.
Okay, will someone in this group come over and explain to this group here how you're getting those values?
Do you have to solve it then?
Okay, what do you want?
They don't know what to do with those numbers.
I know.
I kind of do, but do we have to solve it then? Like,
Okay.
to make it equal to 0?
You put -192 in your y equals.
And then,
Okay.
-192.
Right.
And parentheses x, because you don't have a t variable in there.
oh, so I just
Minus your first time, which is time left.
10
Then you put the 2 parentheses in, and x minus the second time, which is your landing time. Then you get your parabola.
Oh, and then we find that. Okay, I get
Then you find what, Holly?
the maximum or whatever, right?
Why?
Yes.
Because that tells you how high you jump.
The teacher's in-depth content knowledge is evident in her integration of evaluation into instruction. To assess how well the students have learned the concepts she has covered, she has them interpret 2 fictional graphs that display the same kind of data they collected in their experiment. The students have to apply everything they have learned to interpret the graphs.
Here's how I'm going to assess how well you understand what we did. We have 2 people jumping up here, Al and Allison. Tell me what these 2 numbers being different mean.
She landed at a different distance.
She didn't land in the same spot. She landed closer to the CBR or further away? She landed closer. You can tell that by the graph too. Okay? Now, what was her jump height?
345 centimeters.
345. We're still doing inches. 345 inches. Okay, now, I put that up there for a reason. What must have Allison had to do in real life?
She stepped away.
Just step like this way.
She could have jumped out away from it and then jumped in. That would be good. One thing she could have done. What else could have she done?
Held, like jump onto something.
She could have grabbed up onto the lights up there, hung up there, and then landed. 345 inches. That's pretty high of a jump height. So we know that, you know, we didn't do any calculating errors. We didn't have any calculating errors. That something in the experiment had to have gone wrong.